So, if we have y is equal to 2 to the power of x, and I say find the inverse. How do you find the inverse of an equation? You flip x and y. So we flip x and y. We get x is equal to 2 to the y. And then what do? Okay, so you solve for y, right? How do you solve for y in this? That's the y-intercept. I just want to solve for y. Okay, so if I root y, that's not a wrong answer. So if I did this, I still haven't solved for y though, right? I don't have y equals. Problem is, we don't have the tools to do it right now. That's why logs are important, okay? What logs allow you to do is to solve when your exponent is the variable. Now, we did that in the last couple of days when the one I gave you today, when you had something like this. I don't know, 2 to the x is equal to 4 to the x plus 1. We would just make them a common base, right? You can go 2 to the x is equal to 2 squared x plus 1 and equate the exponents. But you can't do that for everything, all right? So you need to use logs. So now we're going to define what the logarithmic function is. So we're going to go down here. We don't need to do a table of values because we know how to graph this. What is the x-intercept of that graph? 1, right? Because x is 0. When x equals 0, or sorry, the y-intercept. Y-intercept is x equals 0, which gives me 2 to the 0, which gives me 1. So I know it goes through 1. What is the horizontal asymptote of this 2 to the x graph? 0. So we have an HA, whoa. We have an HA of 0. Is it growth or decay, this graph? Growth. So the graph looks like this. Y is equal to 2 to the power of x. Okay. If I said graph this, what am I actually asking you to graph? The inverse. How do you graph the inverse without actually plotting all the points? You flip it over the line y is equal to x. Or you switch all the xy points, right? So here's the line. Y is equal to x. This is from the first chapter. So if you reflect this graph over that, 0, 1 becomes 1, 0. And you get this. This blue graph, x is equal to 2 to the y, is actually the logarithmic function. That's the log graph. The log graph is the inverse of the exponential function. Okay? Exponential function graphs look like this or like this. Log graphs look like that. And if we have a horizontal asymptote for the red, the exponential function, this one, of y is equal to 0, where does that asymptote move to on the logarithmic graph? X equals 0, because you switch the xy values. So the logarithmic graph has an exponential function, or a vertical asymptote this time. Of x equals 0. That is for the blue. Yes. All logarithmic functions have vertical asymptotes. All exponential functions have horizontal asymptotes. Okay, flip the page, please. Okay. So the definition of a logarithmic function is it's the inverse of an exponential. You should remember that. But now nobody wants to write it this way. X is equal to 2 to the power of y, because that's just ugly. We want y equals something. So the way you write it is this becomes this. Y equals log base 2 of x. So the 2 is still the base. It's a subscript, exactly. Is it a molecule? Because it's a subscript. So you write it like this. It's like log base 2 of the number x. You can put the x in brackets if you want. Yeah, it's down low. Sorry? Because it's not an exponent, it's a subscript. Subscripts go down. Exponents go up. Or superscripts, if you want to call them that. Okay, so this is the key. The base of the exponential form. This is called exponential form because it's written with an exponent. The base of that becomes the base of your log. It's log subscript, or we would say base 2 of x. Okay, and part of today is learning how to convert back and forth between these. All right, so logs. Couple of things about logs. I'm not going to ask you this, but you'll probably see the words at some point. So y is equal to log base b. B is the base, obvious. The number that you're logging, this x, is called the argument. I'm probably not going to say that ever. I'm just going to say log whatever number, log 4, log x, whatever. But it's called the argument. Just like in exponentials, there are definitions for these terms. So when you have log base b, x has to be positive. You cannot log a negative number, and which goes to the graph on the previous page. It's got a vertical asymptote. The blue graph doesn't go into the negatives. I mean, you can move it if you do transformations, but you cannot log a negative number. If you try to if you do log of whatever on your calculator, it won't work. Of a negative number. Again, your base has to be positive. Can't have a negative base. And it can't be 1. The base can't be 1. All right. Yes. It has to be. By definition, it has to be, because because it's tied to the exponential. So if you look at the exponential here, that would be like me writing x is equal to 0 to the y, which doesn't make sense, right? Okay. All right. So here's our exponential and our logarithmic graph. They write it this way, but really it's just a log graph. Log base 2 of x. That's what that graph is. So we're going to look at the exponential form, and then we're going to look at the logarithmic form. What's the domain for the exponential? 2 to the power of x. What's the all real numbers? So the domain is XER or negative infinity to positive infinity. What's the range for the exponential? We're looking at this one right now. What's the range of that graph? Greater than 0. Or if you prefer, 0 to infinity. Okay. What's the x-intercept of that graph? None. There is no x-intercept because that means you have a horizontal asymptote of y is equal to 0. And what's the y-intercept of that graph? 1, 0, 1 right there. Okay. So for the logarithmic graph, which is this one, what is the domain of the logarithmic graph? It's greater than 0. See, because remember it has a vertical asymptote here. So it's x is greater than 0. And if you remember, the logarithmic and the exponential are inverses of each other. So when you're doing an inverse, the domain and range flip, right? Remember that from the first chapter? So if the domain was all real numbers, then the range of the log should be all real numbers, YER. That's why the range of the original, greater than 0, becomes the domain of the log. What's the x-intercept? 1 and 0, because this point here switches. It's right there.
Might be an extremely dumb question, but what is an asymptote?
It's the point you can't touch. Like it's an undefined point on the graph. Y-intercept? None. NA. And the asymptote, if it was y is equal to 0 in the original, it becomes x is equal to 0. All right. Know the log graph. You need to know the log graph, okay? And the exponential. All right. Are we okay so far? All right, peoples. Okay. Converting between exponential form and logarithmic form. Super important. So we're going to practice this right now. Okay, so here is, let's do exponential and we'll go to log and then we'll go backwards. So here is my exponential form. Whoops. This is the logarithmic form here. What is the base on the exponential form here? No, the base. 2. The base is the number that has the exponent on it. So this is the base. This is the base on the log. Okay? So when you write it in logarithmic form, the base is the subscript when you write the log. Okay? The 1/8 just stays there. And you write log base 2 of an 8 equals, and the exponent now sort of falls down to, I don't know, a regular position, I guess. It's no longer an exponent. Okay, that's why we convert, because it knocks exponents down. So what's my base in 1/4 is equal to 2 to the negative 2? What's the base? 2. So I write log base 2 of what number? 1/4. Now you can put the 1/4 in brackets if you want. And I'll say it in a sec. Equals what? Negative 2. This is the exponent on the original, and that's the base. So the exponent on the original is what everything equals. The base here becomes the base in the log, and the 1/4 just sort of sits there. So what am I going to write for the next one? 1/2 is equal to 2 to the negative 1. What's my base? Log subscript 2 of equals negative 1. Okay? Now we're going to go backwards. I'm just going to put these in. Okay. Now we're going to go backwards. We're going to go from logarithmic form to exponential form. When you're converting back, the base comes over. The base comes over and kicks that number up. So you can see 8 stays the same. The base moves over to become the base, and the 3 becomes the exponent. So what am I going to write here? How do I write that in exponential form? What stays the same? The 4 stays the same. Equals what? 2 to the power of 2, because it comes over and kicks that up. What's the next one? 2 is equal to 2 to the power of 1. And all these make sense, right? They have to make mathematical sense. Like 4 is equal to 2 squared. 2 is equal to 2 to the power of 1. What about the final one? 1 is equal to 2 to the power of 0, and anything to the power of 0 is 1. All right. Are we okay? No? But continue anyway. All right. Flip the page, please. All right, here we go. So, I'm not going to do that. Let's just convert. Okay. We're going to rewrite these in exponential form. So the first one, log base 7 of x is equal to 4. What do I write? No. Yeah. So the number being logged, or the variable in this case, x stays the same. The base moves over and kicks up the 4. X is equal to 7 to the power of 4. What about the next one? 15 is equal to 5 to the power of y. C. What am I writing? B is equal to t to the power of m. Now, this one. We have a number in front of the log. If you have a number in front of the log, you need to get rid of that number. All right? So divide off the 4. Because it's being multiplied, right? So I get 5 over 4 is equal to log base b of 6. Now what do I write? B to the power of 5 over 4 is equal to 6. Okay.
Do you do the square root of that? Like,
No, just leave it like that right now. Okay. Yeah, we're not solving it. We're just practicing going back and forth. Okay. Now we're going to logarithmic form. So, what's my base in this equation? 4. So it's log base 4, so subscript 4, of what number? Of 64 equals 3. What about the next one? What's the base? 2. So log base 2 of 1/8 equals negative 3. What about C? Don't say 2f because that implies that f is an exponent on the e. Okay, say of f. Log base e of f. I know it's a subtle thing, but D. What's my base? A. So it's log base a of 2x plus 4 is equal to 5. All right. Are we okay with that? You're apathetic. Well, you're going to do some practice. 3, 4. See if you can do 7. Don't want you to do 7 right now. Boom, boom. Okay. If you have a number in front of the exponents, all right, i.e., basically that's an a value, you need to get rid of it first. Do not convert to logarithmic form until you get rid of that number. Okay? Because it has to be of the form, it has to be of the form b to the x. You need just your base to an exponent. So I'm going to divide off the 2. So I get y over 2 is equal to 3 to the power of x. Now convert to logarithmic form. What's the base? 3. So it's log base 3 of y over 2 is equal to x. And I strongly encourage you to write your 3, your base, your subscript, whatever you want to call it, down low. And if necessary, put the y over 2 or whatever the argument is in brackets. Because the problem that happens to students is they write stuff like this. What they're trying to write is log base 4 of 3. But what they end up writing is log 4 to the 3. And you'll learn later on, this looks like a totally different answer than what they're trying to write. So write it down as a subscript. Luke.
So, like for a function like that where we got y, we don't have to like try and solve for
No, because there's 2 variables there.
Oh, yeah.
Well, I'll show you an example. I'm going to give you a couple where you actually have to solve for it. Okay? All right, next one. What do I do with the... What do I do? Let's just start over there. Divide by 7. What's my base? 4. Log base 4 of h over 7 is equal to k. Okay. What would you do for d? We're not going to do c. What would you do for d? How do I get rid of the 3 halves? Multiply by 2 over 3, right? Or multiply that up, divide off the 3. So basically it's 2/3 y is 10 to the x. So it becomes log base 10, not 2/3, wow. Log base 10 of 2 over 3 y is equal to x. All right, we're just going to do a couple of these ones. So we're going to solve for y, essentially, or have y equals. So the first one, we got to rewrite it in exponential form. How do I get rid of the log base 7? What do I write it as? Yeah, so the 7 moves over, and I get y over 3 is equal to 7 to the x. What do I do with the 3? Multiply it. So do I get this? Why do I not get that? Yes, you cannot multiply the 3 and the 7 because the 7 has an exponent of x. So you just write 3 times 7 to the x. That is all you can do. That's the same thing. Yeah, like this. That's fine. Let's do C. What do I do? Move over the 5. So I get 7y is equal to 5 to the power of x. And then divide by 7. So you can either write it like this, or you can write it either way. Doesn't matter. All right. Are there any questions about that? No? Okay, I want everybody to go to question 11, please. I will in 1 second. Question 11 on page 228. So, it's asking you to solve for y, like actually figure out the number, okay? So it's in logarithmic form. We need to get rid of the log. What do I do? How do you get rid of it? So you change to exponential. So the 2 moves over and kicks the 3 up. So I get 2 cubed is equal to y over 4. What's 2 cubed? 8. How do I get rid of the 4? Multiply it up. What's 8 times 4? So 32 is equal to y. That's what they want you to do for that one. Like, actually get the number. Okay? Are we okay? Are we okay? All right. Here's what I want you to do. I'm going to go back. There. Okay, we're doing, whoops, 9, 10, 11, 12, 13. No, we're not stopping. 14, 15. So basically 9 to 15. There you go. There is no 16. 9 to 15. I strongly